Okay, welcome to the last episode of Gravitational Waves in a Nutshell. You'll notice I sound a little different this week because last weekend I had a bit of a bout with laryngitis. But what I tell people is that I've been hanging out with, a bunch of old French physicists who drink and smoke, and now I can sound like this. And it's very, very fitting. So a recap from last week. And so last recap, we looked at the Picasso EFT theory of gravitational wave emission from inspiring binaries. We saw that as the post-Newtonian, the classical post-Newtonian approach, it's based on a separation of scales. Black holes or neutron stars are much smaller than the binary, which is much smaller than the wavelength of the gravitational waves. Formally, this hierarchy can be expressed as powers of velocity, and that's the post-Newtonian expansion coefficient. And using aesthetic field theory, one can build a tower of theories which formally do the EFT trick of either integrating out the degrees of freedom, field degrees of freedom, and computing an integrated Fokker action. Or just writing out by symmetry operators that express at low energies the built-in effects of high energy physics. With Feynman rules, power counting, and this machinery coming from field theory, dimensional regularization, some of the computations are easier than they used to be for Einstein, Dilfeld, and Hoffman 100 years ago. There may be a bit easier even than they were for Blanchet and Damour and Deruel 30 years ago. Then we switched to looking at tests of GR, which is a field that is a bit in a holding pattern, I would say. It's eager to do tests with the 100 detections of black hole binaries that we have so far, but it doesn't quite have many actually worked out theories to compare against accurate waveforms. And so it makes do with either consistency tests or phenomenological constraints. But I argue that the consistency isn't worth much because you always find it. And if you didn't find it, you probably wouldn't believe it because of the many different kinds of systematic and other effects one may have. And I also argue that phenomenological constraints are not very interesting because they're written for numbers that have no direct interpretation and no scale. So you may be told that post-Newtonian coefficient 2 is determined to 10%. Okay, good. It's good that we can compute it exactly. In theory, we can. What can we do with that? Okay. In general, to close off on that, if you do tests that require looking at waveforms, you will need a very large signal-to-noise ratio, a very loud detection, because otherwise you don't resolve the fine detail of the waveforms. So for LIGO and Virgo, for instance, where the SNR is of order at best 100, let's say, 20 to 100, which is it's a huge statistical significant with respect to detection, right? A sigma of 100 is incredibly small false alarm, but that still means that you can resolve the waveform to something like 1%. And that means you need a violation of GR that's bigger than 1%, which is, if you're just tinkering around the edges, it's hard to do. Okay, so tests that avoid that, such as dark energy constraints by Filippo and colleagues, that just use the speed of gravity, so the comparison with the time of arrival of the gamma ray burst from the binary neutron star and the gravitational waves, those can be very powerful, okay, because they kind of work around this the problem of looking at the waveform in detail. LISA will have higher, maybe SNRs of 10,000 if we're lucky, if nature is generous enough with the rates of supermassive black holes. So there, that would be both an opportunity of testing now a part maybe in 1,000 or less in the waveform, but also a challenge of having waveforms that are good enough and accurate enough. Okay, so today we're going to talk more about applications of current ground-based data sets and detections. And so in reviewing this literature, which is pretty recent, relatively recent, I was reminded that well, sometimes you go back to things you think you know and you understand, and you find they're not quite what you thought they were or what people told you they were. And so I'll give you my last anecdote from my Parisian stay, which is you know, one thing that Filippo taught me is that you never buy cheese at the supermarket. Okay, you have to go to a proper fromager. And so I did, you know, I go to the fromager and I wanted this one of these little cheeses that you put in the pan. You warm up a little bit and you show me how to do it. No? Okay. So I go and there's this lady who's like this paragon of knowledge of cheeses and the wisdom of 2,000 years of cheese making in her. Although she has a tattoo, you know, on her cheek and a ring around her nose and so on. And so I say, in my broken French, I say, je voudrais un petit fromage ronde pour la poêle. And she looks at me like, this like, it's something that doesn't exist. So she didn't hear right. And she switched it to English, okay? Immediate broken English, but said, no, vous savez, le petit fromage, la poêle, c'est un peu moelleux. And she calls her colleague and says, Monsieur, well, and the other lady also looks at me. It's like I'm from, you know, a different planet and clearly not planet cheese and so on. And finally, they call the boss. Okay, and they tell Monsieur, well, and so he takes me to like a little corner, and there's in one corner, I say, okay, that, and he gives me this thing. So at this point, I don't trust my cheese wisdom and my cheese lore anymore. Probably Filippo taught me wrong that and you should never touch cheese and pan together. So it's a little bit the same, I think, with some of these papers. So you read the title, you think something. You read the abstract, it gives you some suspicions, but you mostly trust. Then you read it through, and you figure out that reality is different, and you just bought something that you didn't think you would, you were buying. So, okay, standard candles. One of the big, it's a big story. It's a big selling point for us, for LISA, for LIGO. There's a big problem in cosmology. We're going to solve it with gravitational waves, okay? Maybe. The Friedmann-Lemaitre, Robinson Walker metric, you know, big success of modern physics. It prescribes and explains cosmological redshift in frequencies. Also, it leads quickly to the idea of luminosity distance, which is if you have a source at cosmological distances, well, for one thing, you're hit by the scale factor, but you're also hit by a redshift 1 plus e twice. Because energy, the quantum itself, is redshifted, if you wish, and because the rate of emission of energy is also redshifted, the d over dt. So then scale factor a squared, r squared, the 1 plus e squared together is the luminosity distance, is the way that things get weaker, let's say, or spread out. Okay, so the way you compute the luminosity distance from a cosmology is that you have to integrate the Hubble parameter to leading order is just redshift over Hubble factor. And that means that if you can measure luminosity distance and redshift points along that, you get a determination of the cosmology. And so that's what standard candles do with various ideas as to sources that you can standardize. And now cosmic tension, right, that's a plot from ACT, is the fact right now that the determinations of Hubble constant and other cosmological parameters from, say, the CMB and from Planck seem to diverge from what you can do with the standard candle hierarchy. And so, which is more on the order of 74, okay, kilometers per second per megaparsec, whereas CMB is lower at 68. So some of you probably have a more updated version of this than I do. So here come in gravitational waves with the idea we can do this with different systematics and by measuring luminosity distance directly. So let's see how. If you do linearize the Einstein's equations again, the thing we did 2 or 3 times already in this course, but this time on a background that is cosmological, you find a very slightly changed version of the usual D'Alembertian equation, and the solution has a familiar shape, just with a scale factor. Here you can write it in terms of the conformal time, but you can renormalize conformal time to where you are, so it really looks familiar. And then that leads to writing basically the same form of gravitational wave radiation equation that we saw in the past, except for the scale factor. But now the quantities that are here are quantities that are measured in the rest frame for the binary. So we do wish to relate this expression to the quantities that we observe. So it's natural, for instance, to insert the frequency observed by buying it out with a redshift factor. And also it's natural to change the distance times the scale factor into a luminosity distance, which is the way that we expect radiation, that we want to see radiation die down in cosmology. So doing that pops out a couple of redshift 1 plus z factors that you can reabsorb in the mass. And so you end up with an expression for the amplitude which has the luminosity distance and which has a redshifted chirp mass, okay, which is the only quantity that we saw mattered in the regular flat space-time waveform. Now, if you look at the phasing, you can do something similar. So phasing proceeds again as a power in time units, let's say, of the chirp mass. So you can again say, well, I want to look at the observed redshifted frequency. And if I do that, I can rearrange my 1 plus z's so that the law of by which frequency grows and the spiral proceeds is written in terms of your local observer time and observer frequency, and the observed chirp mass, which is again the redshifted chirp mass. In short, the waveform that you can use, that you see at a cosmological distance, is the same as you would for a local source, except that you replace the distance with the luminosity distance, and you replace the chirp mass with the redshifted chirp mass. Otherwise, it's the identical waveform. If you had a really long waveform, you may be able to see some stretching that basically the cosmological expansion that happens while the signal is getting to you. So maybe for a 3-year observation of a neutron star with something like a Deci-Hertz space observatory, there's a hope of doing that. And I think Nakamura maybe or other Japanese have tried to see. There's a small dephasing that you could see in there. But otherwise, at this level, for LISA and so on, just this is what it is. In short, if one wants to just give an intuitive interpretation, the idea is that you're seeing a manifestation of just one scale, which is the scale of the size of the binary, basically, the chirp mass or the total mass and so on. And so that is naturally redshifted like everything else. And there's no other way that it could have come out than this, effectively. This is the idea of standard siren, then, that if we measure the redshifted chirp mass and the waveform by way of the phasing, we can compute the luminosity distance, okay? And that's the cosmological luminosity distance that we want to use for the Hubble diagram. And that's the idea of standard siren. We need a waveform. We also need a redshift, though, okay? Because the mass itself doesn't give us the redshift. We just get the redshifted mass. But we do get the luminosity distance directly. Okay, so techniques then to do this, many ideas. Not the original one, but the first one that was actually done in practice was the idea we see a binary at a mild cosmological distance with an electromagnetic counterpart that we can really associate with it. This lets us identify the host galaxy. We look at some optical lines, and we get the redshift. Okay, so this actually goes, I think the proper reference is Holtz and Hughes 2005. Forward, we got one. Okay, just one so far, GW170A17. The original suggestion by Schutz in Nature was actually to say, okay, we get the luminosity distance from the events, and then we have a galaxy catalog. We know more or less where these these sources are. From the catalog, we can get the redshift, if it's a catalog with photometric redshifts, for instance. Okay, catalog should be good though, but we'll see how this works out. Most recent idea is that if we have a distribution for the sources, for the mass sources, for the mass of the sources, let's say, that has a feature, for instance, a kind of peak in the mass, we can fit that together with cosmology, and if you don't have the cosmology right, you smear off the feature instead of compacting it, let's say. Because you should see that peak, at different redshifted values as you go further in distance. And maybe you can use those two things together to do the fit. Or earlier, Chernoff and Finn were saying we can just use an astrophysical distribution. Well, Finn is a gravitational wave guy. Chernoff is more an astrophysicist. So maybe in '93, they didn't realize that it's not easy to compute these things either analytically or with simulations. There are many, many uncertainties. So, because here they mean theoretical distributions, okay? They don't mean observed distributions. This one, we cite it in papers, but I think it's the same really as two. Instead of doing catalog and probabilities, you do a cross correlation of density fields. I think it amounts to the same thing in more of a CMB kind of like language. And finally, last one is interesting, is the idea that neutron stars have a different length scale, which is the idea that they have a radius that sets their tidal deformability, which comes into play in the latest stage of the spiral. We saw in our discussion that this is an effect that is 5pn, so it's suppressed by a factor of v to the 10. However, it's also enhanced by the compactness, so radius over mass. Compactness is 10 for something like 10 for a neutron star. So although it's 5pn, it's amplified by a factor of 10 to the 5, and it ends up being at like a 3pn level, more or less, if one were to count the cycles that are involved. This one, so far, we haven't detected tidal effects yet in any of the binaries, so this hasn't been tried out. Okay, so this was the one that I told you we have, a GW170A17, beautiful counterpart was observed many different ways, from infrared all the way to gamma rays, and it was identified as in galaxy NGC 4993. The distance from the gravitational waves was about 44 megaparsec, so not too far. There was actually, thanks to Virgo, a third detector in the detection and in the network. For one thing, the sky pattern was much smaller than you would get from just the two detectors give you a circle, three give you the intersection of three circles, right, for the three different baselines. But also, thanks to Virgo and to amplitude, kind of like information, we had a good handle on the inclination of the binary, which was almost edge-on, posterior for. No, I think I meant to say face-on here for the inclination. So basically, we almost saw the full circle of the thing, which makes sense because we would have needed to see the GRB, the gamma ray burst from the cone, almost at the polar. So good distance determination, an estimate of the Hubble velocity for the galaxy, with an estimate also of its peculiar velocity in the potential of the galaxy. And with this, you get this kind of posterior, this is against the inclination. This is the posterior of H0 compared with the two things that are in tension, Planck and the standard candles. So it's kind of there in between, it's but it's broad, right? It's a broad posterior that doesn't really solve much here. you can do the reverse. You can say, okay, if I take Planck to be correct, what does it tell me with respect to the inclination of the system? So this is a plot of now h0 against inclination, since it's determined, but it's not determined extremely well. It's determined to maybe 30 degrees, something like that. And also, you may, if you refine your GRB, geometry constraints, you maybe say maybe it's 15 degrees, or maybe you're a little off axis because this was weak, right? This GRB emission. So maybe you're between, I don't know, 15 and 20 or 25. And so you can choose where you are here. You can take different cross sections. This is the Bayesian network for this problem. I copied it over here because I wanted to remind you a little bit about Bayesian networks and the idea that you write all the variables that you observe in gray and the conditional dependencies, probabilistic dependencies that they have. For instance, the observed distance, the observed wave, here we simplify, we leave alone mass and so on, comes from the actual luminosity distance and the inclination. The measured Hubble velocity comes from Hubble parameter, but also from the peculiar velocity. And peculiar also gives us an observation of the local group peculiar velocity. So these are your observables. If you want, you can write, you can use this, writing a conditional for every arrow, and then priors for everything that's left on the top, and you get the total probability. You can look at it, and you can look at the piece that contains the bottom leaves, so the observed ones, and call it a likelihood, call the rest a prior. Or you can use this to write basically a Bayesian conditional posterior for any variable that you like, and this way you don't forget anything. So, yes.
How many more similar events would you need to have something, let's say, good enough to distinguish between the two measurements?
I think at this point, let's just do a Fermi thing here. I think this was a pretty good one. You may do a little better perhaps with the current interferometers, but we don't seem to be getting many events. So let's just say events like this one.
Yeah.
Okay, so full half width, what is it? Half height, full width here is 20 in the Hubble parameter. We probably want like 2, okay, or 3 to square root. So square root of how many do you need to get a factor of 50? A lot. Right, so we have 20, sorry, 10, 100.
So square root of n equals 50
something like that. I mean, more or less they would add like that, unless there's some systematic, or what do you think, Philip?
I vaguely remember 30.
Yeah, okay.
In my...
Okay. It's on a Fermi level is the same. So 30 is a lot, right? Because so far we only got one of these. Now, you know, detectors will get better. We'll see farther and farther. I think we will get there, but not quickly. And so that's why people are thinking about all the other techniques as well. So
maybe
yes.
just concerning further, do we expect to see neutron stars events from neutron stars mergers also at very high redshift, as it is the case for? So what is the highest redshift one could see?
So redshift of this was what? 50 megaparsec is 0.0 something, 0.02,
Yeah,
0.03.
yeah, very low redshift.
Very low. With the current detectors or even the upgrades, maybe you do a factor 2, okay, in distance if you're... I think with the ET or third generation, you can see them pretty far. You can see, because you level the low, it's not just a question of depth in strain, it's also a question of gaining the low frequencies, and so very long integrations of the neutron stars. So there, I think you surely go above 1, I think, for neutron stars.
Okay.
But then you still need the counterpart at the end. Okay, yeah, sure. So okay, so let's go on then to LIGO. and GW3C3, a catalog of 90 binary black hole detections. So what can you do with that? Okay, so one idea is to look at just, you take the loudest 40, something like that, signals that have very good parameter estimation, that very high probability of being astrophysical, and you look at the distribution of the masses, and you see a bump, okay, in the distribution of the masses. The one here, which is basically the Newton star bump, but there's another one in solar masses above at about 30. It also seems to get a little sharper if you just choose a Planck cosmology, let's say, and plot source masses instead of redshifted masses. So the idea is let's try to model this, treat it as a physical length scale or mass scale, and use it together with do a hierarchical Bayesian estimation where I do cosmological parameters and also I do mass parameters that describe a distribution that includes this bump. This is the likelihood for multiple events. There's a normalizing factor here, which is a selection. It corrects for selection effects. So it basically discounts cosmologies, in this case, a mass distribution that would give you too many or too few events compared to the ones that you got. This is my observable, the redshifted mass. And this is the population prior for the population parameters. There's a piece, the rate is considered constant in comoving volume plus a small redshift evolution from some standard scenarios. And then the mass model is similar to what I showed you a couple of weeks ago for the analysis of mass distributions. It's taken either as a truncated parallel, or a parallel plus a peak, or a broken parallel. And one sees that the parallel plus peak is preferred in a Bayesian model comparison way. So the data mildly likes to have this peak. And now you can try to plot then to do all of this together. And so you're fixing the location of this peak, the width of this peak, the underlying parallel, and on top of that, you're changing the cosmology and the Hubble parameter. And so this is the posterior for the Hubble parameter, which is, let's see, the truncated one, which doesn't have the peak, really, gives you a different result. Okay, that's not even trying to do the same thing. The other two are very broad, and they actually like a Hubble of 50, but again, parameter of 50, they're broad. And let's see, what is this? This is a plot of Hubble against the location of the peak, okay, which is preferred around 35, but they're covariant, the two things. We don't have too much data power here to resolve these two variables. And so you can plot the result. It's again curves that don't help too much with the tension, and they're not as strong as the GW 1708 17 result by itself. So all these curves include, okay, GW 1708 17 and that counterpart. And so, this paper even goes to say, okay, with this addition of hierarchical inference from 40 black holes, we improve the uncertainty of the GW 1708 17 by 17%, which I would have found a little sad to write in an abstract, because an improvement of a 20% improvement in the uncertainty is a random walk. I mean, it's something that if we factor 2, I would get, but 1.2 you get just because the data move around a little bit and so on. So this paper, coming into it, I was, okay, let's use black holes to get a Hubble constant. At the end of it, I say, okay, this is like the upper limits paper that we wrote for 20 years before LIGO was on, to kind of like use the machinery and figure out all the inference and so on. But the results are not a lot of bits out of it, okay? So then the other way, catalogs, right? We have the catalog. Let's try to use the catalog. And the idea is that let's take the best we can put together, this GLADE plus catalog made by putting together micron and optical and SDSS and so on. You want catalogs of black holes, of galaxies that have redshifts, photometric with some kind of uncertainty. And so you want a catalog that's reasonably complete going out. The problem is that it's completeness, right? So the estimated completeness here is 20% to 800 megaparsec. And what you care about is a measure of completeness that is the the luminosity completeness, right? Because your basic assumption is that the probability of a binary to reside in a given galaxy is proportional to the luminosity of the galaxy in a given band that is related to star formation and so on. So that said, I didn't know very much about estimating completeness going in. I tried to look it up, and it's like the cheese. It's another universe, right? Where there are papers and papers on estimators on complexity, how you do it. I think this may be almost the way the Hubble did it in 1928, so probably crude, but not great. And now, so you write now a different likelihood, which includes for every event, you try to assign it to probabilistically to the galaxies in your catalog. Except that it's not complete. So for each event, there's also a probability that it's just not in the catalog, and so you have to give it to a diffuse component, which follows just a smooth distribution of masses and redshift. And you use the same. You actually need also distribution of masses because you're doing inference on everything together, which you fix to something that you get from the other piece, from this one. And when you do that, so these are all individual likelihoods for the events. And so what you see on the top are the putative catalog associations. So for each source, these are the hits in the catalog and the kind of likelihood that each of them brings. At the bottom, you see the continuous part, the diffuse part. So you see on top of the actual total likelihood. So what you see is that these catalog associations barely move, except for maybe there's a special one somewhere. This one, for instance. This one is close enough, very good determination. This one has probably some catalog associations. The other ones I basically have a better chance of just being a diffuse component. So this basically means that you get nothing out of this catalog out of 200 parsec. The development of these catalog methods had been partially with an eye to neutron stars, right? And so closer events. These black holes are far enough that it's a hard job to have catalogs that go far enough to see anything. LISA may be different because it's bigger black holes, bigger galaxies. But here, there's no information in this, sadly. Okay, so far. So, and here, again, as we go to my impression is that as you go to next generation detectors, you'll get farther and farther events, but it'll be hard to come up with catalogs that go far enough to give you information. Okay, so that's it. I have a couple more things about LIGO searches, LIGO Virgo, ground-based searches to complete the picture. One is, and there are things we didn't talk about very much, and one is continuous gravitational waves, so things like waves from isolated neutron stars, and the other one will be persistent or stochastic gravitational waves. In LIGO Virgo, there have been for probably 30 years these big working groups, each with their own cultures, dedicated to developing searches and codes for different sources. So one was CBC, compact binary coalescence, which was doing a spiral merger ring down, waveforms, now cosmology is the one that has had the most fun, also the biggest one, with lots of many human hours put into it. Continuous has been a bit of a geeky paradise with the devoted practitioners developing very sophisticated methods because the problem is actually daunting. So yeah, let's get into that. Okay, why? Lots of radio quiet neutron stars in the galaxy, we think, okay, maybe 100 million. They may be spinning rapidly, and if they're spinning rapidly, meaning 100 hertz, maybe even 1,000 hertz, even a very small known asymmetry, a mountain of a few centimeters over 10 kilometers, makes enough of a non-axisymmetric moment of inertia that gives you significant gravitational waves. So the scaling is down here. Same story as we saw, distance, frequency squared, and the quadrupole, basically the moment of inertia of the star, times a parameter, the epsilon, which is the non-axis symmetry, ellipticity, could be of order 10 to the minus 6. That gives you a value, a strain of 10 to the minus 26. So this is smaller than the minus 22, 21 that we were talking about for spirals, but it is something that continues over and over and over. So you can integrate over years, if you have them, of data, and you gain a factor of the square root of the number of cycles in your signal to noise. Still, with all this, you're limited to the galaxy effectively. See the distance here, this is a galactic distance, it's not cosmological or so on. The reason this is difficult is because it is not a monochromatic signal. It's a signal that has let's see, what's the scale here? It's going to have a big Doppler effect from the motion of the Earth around the Sun. It's going to have Shapiro and Einstein delays. And also it's going to have intrinsic frequency derivatives just due to the spin down or spin up in some cases if you have a mass accretion of the neutron star itself. And you have to follow this for hundreds of thousands, actually more, right? Here we're talking billions, right? If we are looking at 1,000 hertz over a year, that's 10 to the 11 cycles. So, and you have to have enough signal shapes to basically find such a wave matching every single cycle. So that leads to, if you were doing a template bank, many different shapes, it would be, I don't know, 10 to the 40, something incredible. So that's where the sophistication come in, and people do it in pieces, and then find ways to combine the pieces together with the maximum efficiency and so on. So this one is the state of the art, just it's on archive. I don't know if it's published there yet. It's all sky, so you have to include for all possible dependencies, Doppler geometries from any position in the sky. It's broad frequency, so it's all frequency. You try every single frequencies and not say just what we think the crab may be at, or so on, for non-axis symmetric neutron stars, but really any signal of any monochromatic signal like this. And so there are competing methods and pipelines to do that. Many rely on short Fourier transforms and then on some kind of transform that then in the time frequency you'd see something like a line or a curve. You want to be able to detect that and to map it onto a parameter space of frequency derivative. And so on. Also some methods, now more modern methods that use short Fourier plus Viterbi, which is a form of local optimization, plus convolutional neural networks for follow-up. And so what you get is a shape that looks more or less like the sensitivity curve for the detector. You see that it's pretty deep, this 10 to the minus 25, okay? And so sky half, the red one, is probably state of the art. Down here, others are a bit are not as good. Okay, so maybe they're computationally cheaper, but not as deep in terms of detection. And you can turn this sensitivity frequency by frequency into the kind of ellipticity into an upper limit. This is probably 95% or 90% upper limit on the eccentricity that a star, if it's there at that frequency, would have. This one is integrated, it's an all sky integral. And you can see that, at galactic distances of 1 to a few megaparsec, you're at an ellipticity of maybe 10 to the minus 6, which is possible. Okay, it could be supported by a crust in a neutron star according to models. It's a bit higher perhaps than what could be supported by the magnetic field alone. It does exclude some models in which you support some eccentricity of the neutron star based on a magnetic field. However, those are based on pulsars that spin slower, so you're not quite in the same parameter parameter range. So these are upper limits. That means also there's no significant detection, okay? For beam by beam, sky position by sky position, you do the usual job of computing a detection statistic and computing a background, and you see that the SNR is not there. This is what the detection would look like. And it's the reason you can show it is because there are hardware injections that are performed on the physically on the mirrors by pushing them at a certain pulse frequency, and actually with I think with the Doppler shifts and all those factors already. So these are kind of internal verification that you could see a signal like that. Of course, they're really labeled and characterized very carefully so that you don't detect them by chance. So you could see it clearly in a time frequency plot. Okay, last one. No, not quite. Is all sky all frequency search for persistent gravitational waves. We used to call them stochastic. Yes, yes, yes.
From an observation of a continuous signal.
Okay, so say you observe one, then you have to explain it. Okay, so this you may be able even to you may see a neutron star there if you do a very deep observation at that position. You may see infrared. In infrared, you may see a neutron star. You may have a decent association. In which case you say, okay, we know that this neutron star has a certain known axis symmetric. It's not just squashed, right? You need the quadrupole, so you need something that's going around. That would be that already tell you something about the crust structure or perhaps the magnetic field. You come up with lots of theories to make it. If you can't associate it, this could also be, for instance, a primordial black hole. If you had a very light primordial black hole of 10 to the minus 5, something like that, that it could orbit a star, a white dwarf or a neutron star, pretty close, and in the galaxy to be a very weak signal since it's very light, and it would not evolve very fast because the mass ratio is very low, so the drag, the gravitational wake is weak. So this search is actually double up also as searches for primordial black holes. If we saw lots or some parallel and so on, okay, then maybe a dark matter search and so on, but we don't so far. Yeah, I think then if you ask them, you know, this paper probably has, you know, 2 columns of reference in astrophysics and so on that goes much deeper than that, but that's my more naive interpretation. Any comments? Someone may know better about this than no? Okay, so stochastic, this is where you don't even try to model your signal. It's not phase coherent. It's just excess power coming from some position in the sky or from the sky as a whole. If it's we do expect, for instance, from a stochastic background from the black hole binaries that are not loud enough for LIGO to see them. And then you can distinguish between a background where you have many that are you know, radiating at the same time as it is for pulsar timing arrays, as we discussed, and more of a background in which they're going through their merger ring down. They're just too far and you don't hear them. So there's just a bit of, they call it a popcorn kind of like noise that in the aggregate makes a background. This also, you know, it's a separate LIGO Virgo group, not too many people, maybe, I don't know, 20 active members over the last very active, yeah, over the last 10 years. And they've been, you know, refining and building sophisticated methods for what is a bit of a an optimistic battle, let's say, that of looking for a stochastic background, because we know that cosmology doesn't really predict anything in the LIGO, in LIGO Virgo band. that has for gravitational waves that would have a chance of being detected, except maybe for some cosmic string exotic scenarios. So you do have astrophysical backgrounds, neutron stars and black holes, but even those are going to be low at the beginning and subordinate to all the individual detections. However, state of the art, past searches have either done the broadband job of doing it at all frequencies together and taking one big integral, assuming either a flat spectrum or a given power law, or look at known positions in the sky, say, I don't know, again, the Crab Nebula or so on, and looked at all frequencies, but just for that one position. The most sensitive search you can do is all sky and narrowband. Okay, so they also call it radiometer, because the idea is that you're kind of pointing a sensitive instrument across dimensions in the sky, across the positions in the sky. It's done again starting from short Fourier transforms, and now there's no template, right? So what you do is you build cross correlations of data between different detectors. 3 baselines now, the 2 LIGOs and the 3 baselines are LIGO 1 Virgo, LIGO 2 Virgo, and LIGO 1, LIGO 2, okay? Livingstone, Hanford for LIGO. A recent achievement has been to be able to fold the data into a single sidereal day, which then makes it much easier to perform successive analysis. And when you do that, you lose something because of the Doppler effect of the Earth motion around the solar system. But at this level of sensitivity and of kind of like geometrical coefficients, functions, and so on, you don't lose very much. And so you build an anisotropy estimator, which is proportional to density of gravitational waves from a certain direction in the sky at a certain frequency. You express it as a basis. The basis could be multiples if you're doing a CMB style expansion, but in this case it's pixels, and it's actually cosmological Hill pix, right? Pixels. And then the estimator looks like the radiometer estimator, known also as dirty map, which is the correlation that you observe weighed by the individual noise in the 2 detectors times an overlap reduction function, which has a phase delay and antenna patterns. This is basically what points this estimator towards a given direction in the sky. And the direction is encoded in the distance, the vector between the 2 detectors dotted into the direction in the sky. Now, this has lots of correlations, and so the correlations are corrected by a Fisher matrix, which has, again, the same ingredients, which partially decorrelates it. It decorrelates it as best as possible. This is familiar, I think, from some CMB mapping exercises, the simplest way you can do it. At this level of sensitivity, actually, there's very little information about the correlations, so one can even take this Fisher matrix as basically diagonal, because most of what you get is noise. And so you also do here the Timeshift game to build a background for this estimator. So instead of correlating data taken at the same time into detectors, you shift it far enough. And you do actually a random shift between to really kill all even long-term low-frequency correlations. You shift all these short Fourier transforms differently as you move forward, and you can see basically that the background and the zero lag, so what you actually observe, sit on an almost perfect Gaussian shape. This is Gaussian if you do semilog in Y, after you've taken out contaminated bins. And by contaminated bins are the parts, the segments of data that either have poor data quality or that have lines, in frequency domain, because they're injection lines, they're noise lines, known violin modes, and so on. By comparison, this is an injection study. And so here the background and these injections that these are again these long-term lines that you put in for the continuous waves these are, they stand up with lots of contrast, really. So this shows that you detect a loud signal here. And here it will this is the SNR plot. So this would be the, at these injection frequencies, these are the high contrast, high SNR events to be followed up. And this is the result. This is the pixel map, frequency index versus frequency. You see the blue goes down. This is the best sensitivity of the instrument in the center. Lots of notches where you've taken out line noise and so on. And these are the kind of maps that you can build. And these go down to, at best, something like 10 to the minus 25 in strain. No detection here, okay? This is, we basically see noise fluctuations around the sky. But at least technologically, this is a very nice search, because from this kind of data, you can build the other ones. So if you want a parallel integrated search, you just sum up effectively data from, not quite the upper limits, but the estimator data from this one. If you want to look at specific points in the sky and so on, you can, all the information is now here. Okay, my very last thing, this is a paper that our colleagues, Tubiana, Babak, Massa, Sokin, I think Tubiana and Osokin maybe now in Germany, but Massa and Babak are very much in France. And this is an update, and it goes to the cheese story again, that sometimes the stories that you are buying are not there anymore. So for LISA, after the first LIGO detection, there was a burst of enthusiasm, because we thought, hey, there's a new class of sources with LISA that opens up. So binaries like this one, the LIGO saw, the stellar binaries of 50, 35, 35, right, solar masses, that would have been seen in LISA if we had it on in the sky 5 years ago, when they were still evolving more slowly in the 10 to the minus 2, 10 to the minus 3, 10 to the minus 1 source. So I didn't put in the archive number, but it's from a few days ago. And so what they did is to take all the binaries from GWTC3, these 90 binary black holes, and to see what they would have looked in LISA, And you can take various scenarios. You do 10 years back, you assume 4 years LISA, 10 years LISA, and so on. So the thing that's surprising and sobering, unfortunately, is that the only one that you could really see is the first one. So the first event was phenomenally lucky, but also very, very, very special. So of all the 90 binary black holes that LIGO and Virgo have seen, there's that one, and there's another one that has a probability of maybe 10 to 20% of that would have been seen with ELISA. And it's a probability distribution because you have to average over sky of the position and the inclination, right, is the one that matters the most. So sky average with different sensitivities, but also inclination. All the others are, not great probability of detection. There are some that come in as a few perhaps as archival detection, which means what? Which means you've done LISA, or you're doing LISA, you observe them in LIGO, and you say, oh, we should have seen it in LISA. You go back to the LISA data, and now since you know what mass it is, where and when, you can use a lower threshold SNR. Basically, you need less statistical significance to see it. But even those are not many, only a few. And then you can see how for one where you do the only one other than GW15 where you can do well, how well you do for parameter estimation, and how much you gain adding LISA to LIGO. You do gain. Because at low frequencies and many cycles, you get better chirp mass and determination, and better spin determination, although not as well as if you have ET, okay, the third generation telescopes. And so, yes.
From the lower plots that the ET breaks some degeneracy? this is
Oh yeah,
while LISA and LIGO are more or less
so okay, so LIGO is a huge it's a huge circle that you didn't even see,
okay.
right? ET would have much higher SNR for the same event because it's maybe 20 times more sensitive, right? Or 10 at least. LISA does give you, yeah, that does break degeneracy. You have error in the chirp mass, but you have less error. Sorry, you have error in the mass ratio, but less in the chirp mass. So okay, together it does help, let's say. Yeah, LISA plus ET especially.
Yeah.
And same story here.
Maybe my question is why the contours are oriented in different directions.
Okay. Luckily enough, I know. Because chirp mass is the leading order effect in the evolution of the waveform.
Yes.
You get it by doing many cycles.
Okay.
And that's what you get with LISA.
Okay.
Low frequency, many cycles, and so on. Mass ratio comes in at higher post-Newtonian orders, and it's an end of spiral merger ring down effect, where you see both masses. And so you do it you do it with LIGO and ET much better because you see the final event for these things which merge in the LIGO Virgo band and ET band and come from LISA. Okay, so then we're revising the science case and so on. There's a bit less. This was known already, but in just from theory and other estimations. But I think that this paper was very timely. Great idea to do it because it's very visual. We take those 90 things, GW3, C3, and that's what we have. Yeah, so let's hope for the massive black hole binaries. Okay, so that's all, folks. Thanks for sticking with me these 5 weeks, and it was fun. I learned a lot by looking at things again, some of them, and that's it. Keep do right. I leave I leave this afternoon actually for Italy though, not for the US, but I hope to visit again in the future, and since I love it here, and so thank you.
So you discussed about a stochastic gravitational wave background for LIGO, yes, LIGO Virgo. I know that in LISA it's a huge business. I mean, there is a huge community working on that. So can you say more since you?
For sure, there's a huge community, and with the friends and colleagues like Chiara Caprini has been one of the leads of the working groups and so on, concentrated on early universe, phase transitions, inflation scenarios, and there are certainly, you can come up with many signals, and LISA is in an interesting spot, right? The electroweak transition.
But there is also a community.
Now, the thing is, from the data analysis side, it's been something that has not been exactly swept under the rug, but it's been kind of held in wait for a little bit, because you really need to do it after you've done everything else. So it's you need to clean your signal from your data from all the other signals you're going to see. As well as you can, which includes the black holes, maybe the M rays, although they're not as loud, the galactic binaries and the foreground of galactic binaries. And then after you've done all that, you can you'll have a background of a residual that you need to explain, either of just pure noise from the instrument or pure noise and cosmological effect background. So we have rough ideas how to do that, but we don't have really a demonstration, for instance. So there are codes to extract spectra, but they're still looking at very idealized cases, either that you do know the instrument noise, or you know the spectral slope of the gravitational wave background you see, and it's significantly different than the instrument noise, and so on. So I would say it's still an open problem, maybe a worry in the back of many people's minds, and we certainly need to try to do our best to match the theoretical effort that the cosmologists and theorists have done. But maybe some of you have a better idea, but I don't have a very clear picture of how a confident detection could be made of such a background. Now, it could be loud enough that if we turn it on and see an overarching constant omega foreground above everything, fine, okay, that would be easy. Okay, the trick is to do it at the level of the sensitivity of the instrument. And so, yeah. So hard question, Filippo, sorry, but tough question.
So regarding cosmological parameters, it looked like the first kind of strategy that you outlined was the most promising, the one with the optical counterpart and everything. Yes. So can you also get an optical counterpart from neutron star black hole events or no?
We haven't seen one so far, but of course people are following up those events, and the expectation is that you'd want a small black hole for that, because if it's big enough, you'll probably just eat up the neutron star in a direct plunge, and there wouldn't be much time or space for a counterpart. If you have a smaller black hole, say, I don't know, 5, maybe 10 solar masses, you would get a tidal disruption instead of the star around it, and maybe you can compress it enough to maybe not get a GRB, but some kind of optical kilonova-like event and so on. So it's not my expertise. I'm sure there are like 30 papers about it if you start digging into it, and yes, those events, alerts go out, and all the various networks of telescopes do look for those, and those are a few more, right? So we've had 2 binary neutron stars. There's something like 5, maybe 4 or 5 intermediate events. So we'd have better rates, but yeah. Thanks. But the rates get better because the black holes are heavier, so they're not exactly the one you want, perhaps, to get the fireworks. Yeah. Good. Thanks again.
Thanks, Michele.